neuron classifications, type A, B, and C from chapter 11. Preganglionic autonomic neurons are what class? A, B, or C? Preganglionic. B. And that's because they have a little bit of myelin. How about postganglionic autonomic fibers? They're type C. Because they have no myelin at all. Of these two, the type B, the type C, which one is going to have the larger diameter? What type of information travels along type A fibers? Somatic motor and somatic sensory. And then B and C, just if we kind of combine them as a group, visceral motor and visceral sensory. Now, somatic sensory, though, was listed twice. Once under type A fibers, specifically type A delta, which is the slowest of the type A's. And then it was also listed under C. And what was that specifically I'm referring to? Pain and temp. So then the question was, well, how can pain travel along two different neurons and temp travel along two different neurons? Why would that be the case? Because there's different types of pain information and there's different types of temperature information. And the simplest way to put it, if it's old information, it travels along the slower pathway, type C. New information, a sudden change in either temp or pain, travels along type A fibers. So that dull chronic pain that you feel all the time, type C. You cut yourself, you burn yourself, some sudden new pain, type A. And it feels different, right? The type A is like the sharp burning sensation, and the type C is that achy, dull sensation. And then same with temperature. Status quo, yep, same temp, monitored all day long, just, your environment is staying relatively the same. Type C. Sudden change in temperature, type A.
When it comes to myelination, for the type B, that's all Schwann, and for type A, that's all of the whatever?
What matters as far as that, where is the neuron? If it's in the peripheral nervous system, then it's Schwann cells. If it's in the central nervous system, it's oligodendrocytes.
Okay.
That's all, just location. Now naturally, that sparked a little thought. This is how you're studying at home. Oh, glial cells. Well, what are the glial cells of the CNS? You just brought up a glial cell. How many are in the CNS? What are they called? What do they do? This is how you study, right? But I'm not going to go there. But you should, later. So we did resting membrane potential, action potential, graded potential, EPSPs, IPSPs, neurotransmitters. Trying to all the major physiology stuff from 11 first and foremost. What else?
Neurointegration or chemical or
Electrical
electrical synapses?
synapses are rare. That's where the presynaptic neuron and the postsynaptic neuron have their membranes joined by gap junctions. So when the action potential travels down the presynaptic cell, it jumps, so to speak, to the postsynaptic.
Do we need to study that?
It was just a brief little blip, just a single little phrase mentioned on the study guide. What most synapses consist of is a chemical synapse where the presynaptic membrane is not attached to the post. There's a little separation between them, albeit small, it's nanometers. They're close, but they don't touch. One has to release a chemical that binds to receptors on the other. So presynaptic membrane releases neurotransmitter, postsynaptic membranes have receptors for that neurotransmitter. And then in turn, when the neurotransmitter binds to the receptor, it's going to open ion channels. When you open ion channels, ions start moving across the membrane, changing the voltage. If that voltage becomes more positive at this postsynaptic membrane, we call it an EPSP. And if the voltage becomes more negative, we call it an IPSP. I got one. Summation. Graded potentials exhibit summation, action potentials, there is no summation. In fact, what's the only thing you can change when it comes to an action potential? The only thing that varies, frequency. For a graded potential, quite a few things can vary, right? How strong it is, how far it travels, whether it's excitatory or inhibitory, which ion is causing the change in voltage. There's a lot of variability. Well, let's compare and contrast. What channels are used to generate graded potentials? Ligand-gated or mechanically gated. And action potentials? Voltage gated. Graded potentials decay over distance. But the stronger it is, the further it travels. Action potentials. They do and they don't decay. See, one single action potential generated at the membrane, we can go back to the hillock here. I'm going to break up the membrane into segments. So when the graded potential reaches the hillock, and that initial segment, which is one name for it, is depolarized to threshold, the voltage-gated sodium channels open, sodium rushes in, spreads to the left, and spreads to the right. And when it spreads to the right, it does decay over distance. And if there weren't another batch of voltage-gated sodium channels right here, if they were, say, over here, that action potential may not make it that far. But the reason why we say action potentials don't decay is because they're propagated. They're self-regenerating, self-renewing. So it isn't as though one action potential is produced and it somehow travels down the entire axon. That's not quite how it works. That first one is produced, and right next to it, it generates a second one. And right next to that, it generates a third. That's propagation. So as it spreads to the right, depolarizing this segment, causing sodium influx, which spreads to the right and spreads to the left. Why is it when it spreads to the left, this membrane doesn't undergo an action potential, but this membrane does? The membrane to the left is in refractory because it just underwent an action potential. And it's probably still in the repolarization phase or the hyperpolarization phase, but it hasn't returned to rest yet. It's in a refractory period. But to the right, that membrane is at rest. And so just a regular threshold stimulus, 15 millivolt stimulus, is enough to do the trick, right? And open the next batch of channels. So refractory. Be able to mark it on your graph and explain what's happening. So where do we start the absolute refractory period? The deviation from rest. The same place we are going to start the phase called depolarization. It's really from -70 all the way up to +30. Now we don't transition from absolute to relative at +30. What is the approximate voltage where we transition? Threshold, pretty close to it. Somewhere in here. Now I'm often reluctant to connect it to threshold because that might give you the impression that reaching threshold is what causes the change from absolute to relative. Threshold has nothing to do with it. So what I often say instead is, to 2/3, 3/4 of the way through repole. More than halfway through repole. And then where does relative end? Back at rest. So refractory starts when we deviate from rest and ends when we're back at rest. But there's two refractory periods, absolute and relative. Each one occurring for a different reason. How many reasons do we have for absolute? 2. So we're going to break it up into depolarization, and then that first 2/3, 3/4 of repolarization. During depolarization, why can't we generate an action potential no matter how strong the stimulus? The channels that you need to open in order to generate the action potential are currently opening. That sodium current that you need to generate that action potential, you already have, right? You're in the middle of it right now. Now, once that's over and we close the channels, sodium influx, the open voltage-gated sodium channels, is no longer the reason for absolute refractory. Now, it's a different reason. Why is it we still can't generate an action potential no matter how strong the stimulus? Yeah, not enough voltage-gated sodium channels have reset. So the thing about the 2 gates on the sodium channel, it leads to 2 closed states. There's closed and capable of being opened. There's closed and incapable of being opened. You could say closed and active, meaning it can be opened, and then there's closed and inactive, can't be opened. So resetting is going from one closed state to the other. So tell me what the closed state looks like when it's incapable of being opened. The activation gates are closed, and the inactivation gates are open. Good. And a channel that's closed but capable of being opened? Activation is closed, inactivation is open. I can say it again. Okay, so closed and ready to be opened, reset, means activation is closed, inactivation is open. Closed and not capable of being opened. Inactivation is closed, activation gate is open. I can draw them. So that's a closed activation gate and an open inactivation gate. Open activation, just not going to draw anything in the middle. Closed inactivation. Now, in order for the channel to be open, both gates have to be open. And in each of these scenarios, one of them is closed. But it does matter which one. So this is the one that's ready to go. So upon hitting threshold, and this is what we wrote on the board, the activation gate opens immediately. The inactivation gate slowly closes. So that thing pops open, sodium is rushing through as the inactivation gate slowly closes. How long does it take for it to finally close? 0.5 to 1 millisecond. The same time frame it takes for the voltage-gated potassium channel to open upon reaching threshold. So they kind of do their thing at the same moment. Voltage-gated sodium channels are closing at the exact same time voltage-gated potassium channels are opening, and both of those events were triggered at threshold. We both have the same delay. The only thing that happens immediately is immediate opening of the activation gates, which allows that sudden immediate influx of sodium. So ready to go versus can't be open. So which one of these two would be considered reset? Ready to go. So during most of repolarization, there simply are not enough voltage-gated sodium channels reset. But the longer we wait, the more are reset. So once you transition into relative refractory, you can generate an AP now, but what does it require? A supra-threshold stimulus. So we have a graph that shows the changes that are occurring to the sodium channels and the potassium channels and the size of the stimulus required to generate the next action potential. So on that graph, we have strength of stimulus. So during rest, it's just a regular threshold stimulus, like 15 millivolt threshold stimulus to from -70 to -55. And then once you get into the absolute refractory period, there is nothing written on the graph because there is no stimulus strong enough. You simply cannot generate an action potential. One way to remember this, you absolutely can't generate an action potential during the absolute refractory period. You can generate an action potential during relative refractory, but it requires a relatively stronger stimulus.
Is that where an EPSP would come in to help generate?
Yeah,
potential?
that is the stimulus.
That is the stimulus.
Yep. That's the thing that has to be greater than threshold.
Got it.
Has to be super threshold. All right, so the other thing, when we get into relative refractory and we need that super threshold stimulus, it's not the same all the way throughout the relative refractory period. And so this will mark the end of relative refractory. We're back to rest, which means, once again, a regular threshold stimulus will do. So this is showing the size of a threshold stimulus. Which is an EPSP of 15 millivolts in size. That's what has to be at the axon hillock to get us from rest to threshold and generate that AP. But that's when the membrane is at rest. During the action potential, it's not. So that changes things. So before the action potential begins, threshold stimulus. Once it's over, back to a threshold stimulus. During absolute refractory, no stimulus is strong enough, so we're not going to draw anything on the graph. But during relative, you need a suprathreshold stimulus. But the longer you wait, the less suprathreshold it has to be. So it's not the same throughout. Which means the stronger the EPSP, the earlier in the relative refractory period that you can generate the next action potential. This is why bigger EPSPs generate action potentials at higher frequencies. The earlier you can generate the next AP, the higher the frequency becomes. So bigger and bigger EPSPs cut into the relative refractory period more and more, allowing you to generate the next action potential sooner and sooner, which means the frequency is going higher and higher and higher. So to put all of that together with an example, Pacinian corpuscle, pressure receptor. A little bit of pressure, you open just a few mechanically gated ion channels. You generate a small EPSP, maybe just strong enough. Maybe it's a threshold size stimulus, just strong enough to generate an action potential. But when is the next action potential going to be generated with that same size stimulus? If it's exactly a 15 millivolt stimulus, it's just a threshold stimulus, when will the next action potential come through? When the first one's completely over, right after the hyperpolarization phase. So this could take 15 milliseconds. So that means you have a frequency of 1 action potential every 15 milliseconds. That's pretty slow. But then you push a little harder on that Pacinian corpuscle. You open even more mechanically gated ion channels, even more sodium influx, and even stronger EPSP. Now super threshold. So now instead of having to wait 15 milliseconds for the next one to come through, and you're pushing on it, you're not just pushing and letting go, you're maintaining the stimulus. And this is why you get action potential after action potential, right? So based on the pressure you're applying, you get a certain strength, a certain size EPSP. And it keeps reaching the initial segment of the axon, and it keeps triggering the next action potential, one after the other. But if I just push a little bit more, and it's just a little super threshold, yeah, I don't have to wait the full 15 milliseconds, now maybe 13 milliseconds, now maybe I'm here. So the frequency went up a little bit. Push even more mechanically gated ion channels open, more sodium influx, and even stronger EPSP. I can cut into the next relative refractory period even sooner. So now I'm 1 every 12 milliseconds, 1 every 10 milliseconds. If the absolute refractory period is 1 millisecond, what's the highest frequency I can generate? 1 action potential every millisecond, right? Because that means I could start the next AP as soon as absolute's open. If that EPSP is strong enough, if I'm pushing really hard on that Pacinian corpuscle and I'm opening all the mechanically gated ion channels, maximum sodium influx, my EPSP is as strong as it can be, and let's say it's this strong, I don't even have to wait for relative refractory, right? As soon as it starts, boom, next action potential. That's a really high frequency, 1 every millisecond. So depending on how hard I'm pushing on that Pacinian corpuscle, I'm somewhere between 1 every 15 milliseconds and 1 every 1 millisecond. That's rate coding. So this information, these signals, are going to the same place in the brain, to that little map, the homunculus, in the primary somatosensory cortex. And that's how you are able to perceive location. That's how you know that we're pushing on the left index finger. Right? So location is based on where those action potentials go within the primary somatosensory cortex. The frequency, when they get there, is what allows you to perceive intensity. The higher the frequency, the stronger the stimulus. Right? As far as you're concerned, that's what you feel, that's what you perceive. More pressure. Colder, hotter, more painful, more pressure, more of whatever, right? At a higher frequency. That's rate coding. Also chapter 11. So we have 2 reasons for the absolute refractory period. During depol, the channels we need to open are already open. During repol, simply not enough voltage gated sodium channels have reset. Relative refractory. Now, enough voltage gated sodium channels have reset, but not all of them. Until you have all of them, you're gonna need a suprathreshold stimulus. You still have all this potassium leaving, and you have to overcome it by bringing at least the same amount of sodium in, right? Really more. Wow.
It's just itself off and clean.
It's all good. Clean away, my friend. Thank you. Appreciate your service. So 3 reasons for relative refractory. 1, although you have enough voltage-gated sodium channels, you don't have all of them. And the other 2 reasons have to do with potassium. So what are they? I was asking why the sky is blue. Oh, done, me out. Just reminded that we got more.
It's cold now, you got another one.
Oh, doesn't matter. I'm good. I'm a fiend. My crack doesn't have to be hot. Cold crack's fine. Especially when it tastes good. Good crack. That's why I said that. I think I lost everyone some time ago. We were talking about the reasons for the relative refractory period. I gave you the first one. I said the other 2 have to do with potassium, and then I asked you what they were, and then I heard crickets.
That was the machine.
Oh, sorry. And then I was reminded I needed more crack, and so that's right.
Okay, so in addition to potassium, the leak channels, you also have the channels open, so you have too much potassium preventing depolarization,
Right?
and then that's also causing the membrane to be hyperpolarized.
Right. So we're going to break up the excess potassium efflux into two problems. One, just the fact that you have all this excess positive charge leaving means it's going to be that much more difficult to depolarize the membrane. You have to bring that much more positive charge in, which is sodium, which means a stronger graded potential, right? That's the source of sodium. It's the graded potential. Until we engage that positive feedback loop where the voltage-gated sodium channels are letting all that sodium in, until that happens, it's all coming from the graded potential. The other problem is, with all this excess potassium efflux, the membrane's no longer at -70. It's at a value less than that. The membrane's hyperpolarized. So even if you had a threshold stimulus, a 15 millivolt stimulus come through, if you're starting at -80, that 15 millivolts will get you to -65. You're still 10 millivolts away from -55. You're not going to hit threshold. So just the fact that you're starting below -70 means you have to have a super threshold stimulus. It can't be 15 millivolts. It's got to be at least 25 now, right? If you're starting at -80. But that still may not be enough because you still have to account for the excess potassium leaving, and it still may not be enough because you may not have all your voltage-gated sodium channels reset. Now, one happens before the other. Do the voltage-gated sodium channels reset before all the voltage-gated potassium channels close, or the potassium channels close and then you get all your reset voltage-gated sodium channels? You didn't want to say all those words, you're like the first one. The voltage-gated sodium channels reset a little bit before, a few milliseconds before the voltage-gated potassium channels finally close. So, the longer we wait, the suprathreshold stimulus doesn't have to be as supra because, one, we have more voltage-gated sodium channels reset, two, more of our voltage-gated potassium channels are closed, and three, assuming we're over here now, the membrane is getting closer and closer to threshold. Right? All right, what's next?
When you say, like, functional groups, neurons are organized into pools or functional groups and circuits?
So at the most, one question on the exam. Maybe zero, but at the most one. I didn't want to mark it FYI, but I didn't want to make a big deal about it either. The main ones I wanted you to know was convergence, right? So you have information coming from separate neurons, several different neurons, all being conveyed to one neuron. Divergence is the opposite. One neuron can send the same signal out to many different neurons, many different circuits, many different parts of the brain. That's divergence. So one example of divergence would be when those upper motor neurons send their signals down to the lower motor neurons. Not only do the signals go down to the lower motor neuron, but there's a collateral that comes off of the upper motor neuron and heads back to the cerebellum through the middle cerebellar peduncle. So the cerebellum is receiving the same message that the lower motor neurons are receiving. The cerebellum therefore knows what the muscles should be doing. And what is the cerebellum comparing that to? What is actually happening? And how does it know what is actually happening in terms of that movement that you're performing? Proprioceptors. Constant proprioceptive input back to the cerebellum lets it know what's actually happening while you're tying your shoe or reaching for that container of milk or shooting the free throw. So you get real-time corrective signals going back to the motor cortex and then back to the motor units, to fine tune that motor task. But that would be divergence. One signal from the upper motor neuron going to two places, the cerebellum and the lower motor neuron. They're both getting the same signal.
And that's the divergence.
Say that again.
That's divergence.
Divergence.
So what would be like a case of convergence?
The prefrontal cortex receiving signals from all parts of the brain. Primary visual visual association areas, sensory association area, all these association areas, all of that goes to prefrontal cortex. That'd be convergence. And then we have the reverberating or oscillating circuit. Those are involved in rhythmic activities like breathing or locomotion, and even just keeping the cerebral cortex alert. What gray matter in the brainstem has these reverberating circuits and is keeping your cerebral cortex alert while you're awake? We just covered it yesterday. It's that loose collection of nuclei scattered throughout the entire brainstem, midbrain, pons, and medulla. 2 words. First one starts with an R, second one starts with an F. Okay. So within the reticular formation, there is something else that has an acronym that has those oscillating, reverberating circuits. RAS, Reticular Activating System. So what's going to shut down those reverberating circuits so that you can transition from alert cortex to a sleep cortex, where you're literally asleep and no longer paying attention? Tranquilizers, sleep-inducing drugs, right? Or if you just want to do this naturally, you fall asleep late at night. Right? You get tired and chemical changes occur in your brain. Because you have your own sleep-wake cycle that's being regulated by your own brain, right? We don't have to take medications. Well, some people do, but you know what I mean. Yeah. We can get a little extra help when needed. We can quiet down those reverberating circuits and help us transition into that sleep state. All right, I have some questions for you.